Hello everyone, in this video I will explain Gibbs free energy using enthalpy, entropy, and temperature and how they affect the free energy of a system. Then we will look at how we can explain the spontaneity of a reaction with a Gibbs free energy. We will also apply this information on real-world examples such as the phase transition of melting of the ice. So let's start with enthalpy. As you might recall, enthalpy in simple terms is the sum of the internal energy and the product of the pressure and the volume of a thermodynamic system. If we consider the enthalpy of a reaction in a broader perspective, we should look at the reactants and the total amount of energy we need to break the bonds of reactants to form products. And the energy released in the products is shown as the negative bond energies. So if you put reactants and products with their bond energies, let's say on a balance beam, and let's say if there's more reactant energy consumed, so there's more energy here, or in simple terms, if the system gets heat energy from the surroundings, this is going to be an endothermic reaction. Whereas if there's more energy released to the surroundings, this is going to be an exothermic reaction. Returning back to how this is related to the spontaneity of a system is that as the system of a reaction gives off energy, there's a decrease in the amount of internal energy. So as we lose internal energy, we expect a decrease in the enthalpy of a system. Decrease in enthalpy indicates the favoring of products, thus it indicates spontaneous reactions. And increase in enthalpy indicates non-spontaneous reactions. Let's do a simple example. There are many techniques to measure the amount of heat involved in a chemical or physical processes, but my favorite one is known as calorimetry. Calorimetry is one way to measure the amount of heat transferred to and from a substance. Using this approach requires the definition of a system and its surroundings. Knowing the heat capacity of the surroundings and taking careful measurements of the masses and temperature before and after the process allows one to calculate the amount of heat transferred. Well, this is just a reminder of a way of how we could calculate enthalpy of a reaction, but that is not the focus of this video. Now, let's look at the melting of ice. The molar enthalpy of fusion for ice at 0 Celsius has an accepted value of plus 6.01 kilojoules divided by moles. Since this reaction's products are higher in energy than the reactants, the change in enthalpy is positive. So the fact that the enthalpy is positive is a clue that this is going to be a non-spontaneous reaction, right? Not so fast. It turns out that even though the reaction of melting ice is an endothermic reaction, it is indeed a spontaneous reaction. In the next slides, we will review the concept of entropy and temperature to understand why. But the important key takeaway from here is that enthalpy per se does not indicate the spontaneity of a reaction. So what is entropy? Well, in simple terms, entropy is a quantitative measurement of the randomness of a system or the amount of spatial and energetic states available to it. Now remember, the second law of thermodynamics says that the entropy of any isolated system always increases. For example, let's look at this example. There are two isolated spheres. And on the right sphere, there are some gas molecules, and on the left, we have nothing. It's empty. So if we were to open the vacuum in the middle, what is going to happen? Well, the gas molecules will shift towards the empty sphere, increasing the entropy, even though there's not really any change in the temperature. Recall that as the entropy increases, the reaction becomes more spontaneous. Thus, increase in entropy and decrease in enthalpy together favors the products or spontaneous reactions. So when considering the spontaneity of a reaction, we should also consider the entropy. Okay, let's continue with our melting ice example. A spontaneous endothermic reaction can occur when the changes in enthalpy and entropy yield a negative Gibbs free energy. An endothermic reaction can be spontaneous if entropy increases by more than the change in enthalpy. Ice initially has a low entropy, but as ice melts, the intermolecular forces are broken, which requires energy. But the order is interrupted, so the entropy increases. Since water is more random than ice spontaneously melts at room temperature, which is 25 Celsius. Okay, so far so good. So I want to challenge you with a simple example to foster your learning. Can you calculate the free energy of the ice melting at a temperature of 25 Celsius? The delta S and delta H is given. Well, I hope you got the answer right. As we can see, it was possible for a reaction to be both endothermic and spontaneous. But let's make things a little bit challenging. How important do you think the value of temperature is here? Can it really affect the spontaneity? Let's figure it out. The temperature plays an important role in determining the Gibbs free energy and spontaneity of a reaction. The value of delta G is dependent on temperature. Sometimes changing the temperature can change the sign of delta G. And this explains why some reactions go in one direction at one temperature and in the opposite direction at a different temperature. Continuing with the example of melting ice, we can see that instead of melting our ice in a room temperature, if we were to melt it in a minus 10 Celsius environment, let's say like in a fridge, our reaction would be non-spontaneous. You can calculate it to confirm this. But the main key takeaway is that free energy can either increase or decrease for a reaction when the temperature increases. But keep in mind that whether it's going to increase or decrease depends on the entropy as change. We will understand why in a minute. Also, before we move on, it's critical to understand that Gibbs free energy is only applicable for systems under constant temperature and pressure. So let's wrap things up. We know that the Gibbs free energy calculates the relationship between enthalpy and entropy in a system to determine the spontaneity of a process. But how exactly are we supposed to know the spontaneity of a reaction? Well, consider the following table. We already know that exothermic reactions with increased entropy are always spontaneous, and endothermic reactions with decreased entropy always have non-spontaneous reactions, which are shown by the upper left and lower right boxes, respectively. The lower left box shows that for exothermic reactions with decreased entropy, we determine the spontaneity of a reaction based on the temperature. We know that it is spontaneous at low temperatures, so it must be non-spontaneous at higher temperatures. Now consider the upper right box. It shows that endothermic reactions with increased entropy are spontaneous reactions at high temperatures. Does it remind you of something? That's right, our beloved ice melting example. Since the Gibbs free energy for ice melting is smaller than zero, this is again a spontaneous reaction. So this table sums it up. Well, this is the end. I hope this tutorial helped you to clarify the fact that the enthalpy of a reaction alone is not sufficient to determine whether a process is spontaneous or non-spontaneous. And there's a temperature of inversion from a non-spontaneous process to a spontaneous process. And the other aspects of thermodynamics, such as entropy and temperature. Thank you so much.